Hi, I'm going to talk about my bachelor's project, which is to try and understand what two-stream convolutional neural networks for action recognition are learning. So, convolutional neural networks are a form of supervised machine learning model. They're very large models. They're composed of hundreds of millions of parameters, so we have to train them on GPUs, and they're traditionally used for object detection. So over the past few years they've achieved state-of-the-art results in object detection and localization. However, their use in videos, for example for action recognition, which is trying to infer what actions someone in a video is performing, their results are not quite so good yet. So the reason for this project is to gain a greater understanding of what these networks are learning, so we can then use that insight to inform future architecture developments. So the first thing I'm going to do is just go through what a convolutional neural network, or CNN, is, and then I'm going to discuss some of the analytical techniques that I've looked at for potentially analysing these networks that I'm looking at. So in the left-hand corner we've got a diagram of a CNN. So each of these blocks represents a layer, and layers have they're generally 3D. So here we've got a 224 by 224 by 64 block sized layer. The first two dimensions represent the width and the height of the layer, and the final dimension, so in this case 64, represents the depth of the layer. For convolutional layers, the depth specifies the number of filters that we're learning. So in this case you'll learn 64 filters, and those are 3D filters that we convolve with every input region in the image. Pooling layers, which are these red layers here, are layers to reduce the dimensionality of the previous layer. So, for example, max pooling looks at a pixel region 2 by 2 and propagates the value, the largest value in that region. So as you can see, as we go through the network, we successively reduce the width and height dimensionality, squashing it into the what's called the channel dimension, until we end up with a 1D vector. In this case, the output of the network is 1D with 1,000 elements. So those 1,000 elements represent 1,000 different classes. So most of these networks are trained for object detection, and that's what all these analytical techniques here have been used on. They've been used on networks for object detection. In the top right-hand corner here we've got what's called an ablation study, and the idea behind this is we want to find out how the activation of a specific output neuron varies as we occlude certain regions of the image. So we've got this grey square here, and what we do is we slide it along occluding different parts of the image, and we plot how the output neuron activation varies over time. In this case we're looking at the activation of a neuron that fires for people. So as we slide it over and we occlude the faces, you can see the neuron doesn't fire so heavily. So this can actually be used to localize objects and images as well. These two diagrams represent the results of applying a deconvolutional network to a network under analysis. So a deconvolutional network can be constructed from a normal convolutional network, and the idea is that we want to reverse the operations of the network that we use for prediction, so that we can go, in this case, backwards from a neuron to the input space, the image space. So in this diagram here for layer 2 we've got a bunch of patches. So each of these little patches represent the input space that maximally excites a specific neuron in layer 2. So as you can see, they're quite simple, mainly edges and certain blob shape patterns. We've got some corners down here. The reason they're smaller than the layer 5 patches is because the filters have a smaller field of view because they're quite early on in the network. The area in the input region that they can see is quite small. As we progress further through the network, once we've pulled down and aggregated results from previous layers, when we propagate back through the deconvolutional network, we end up with larger patches. So you can see that these activations from layer 5 represent much more complex features. In this case, they're this neuron is recognizing eyes. This one here is recognizing cat's ears. I'm not sure what this is recognizing. This next technique is one that uses a type of network called a deep generative network, and deep generative networks are trained to invert the representation of an image deep in the network. So for example, one of these layers here, so for example, these images were generated on a network trained to invert AlexNet, which is a type of object detection network, and they invert from FE6, which is this layer here, back to the input image. So the idea is that from a specific code at this layer in the network, what input image would produce that code. And what these people did were to extend that idea, and for an arbitrary neuron in the network, try to figure out what input image would maximally excite that. Now, people have attempted this before by just performing gradient ascent on the input of a network. However, you end up with salt and pepper noise generally. The way we produce realistic images is by tacking on this deep generative network at the sort of beginning of our initial network, and this essentially acts as a prior to enforce realistic looking images, and you can see the results here are very effective. So the action recognition networks that I had available were initially Bioid, which is a network, it's a data set of videos shot on body, which is what egocentric means. So these are shot from cameras like Google Glass. And this data set is of people performing actions. So here you can see they're quite short clips, so someone picking up a plug, someone opening a jar. And what's challenging about this dataset is that the viewpoint of the camera changes quite rapidly. So initially I tried investigating excitation backprop on this, and we'll have a look at some results of that in a minute. There's also a well-known dataset called UCF-101, which is from the University of Central Florida, and this is a set of 101 categories of actions. And those actions are primarily shot from static cameras, although as you can see from this football example, there are some dynamic camera movements. This is probably an easier data set to interpret the results from, so after trying some experiments on Bioid, I actually moved to UCF-101 to see whether, to try and interpret my results more easily. Action recognition networks are composed of two streams, which are effectively two separate networks. This is an architecture from 2014 designed by Karen Simonyan and Andrew Zisserman. So one network looks at a single frame. So you can see here we're looking at an archer drawing a bow, and another stream or another network looks at a stack of optical flow. So a stack of optical flow is a sequence of optical flows, flow pairs. So we calculate optical flow in the x and the y direction, and then for t consecutive time steps, we take those flow pairs and feed them to the network. So this network is essentially getting a little snippet of optical flow video fed to it. And previous results have shown that the temporal stream is much better at recognising actions than the spatial alone, but combined they have better performance than on their own. So down here I've got some results of using excitation backprop for the spatial network for Bioid. So it seems to learn the location of certain objects in the environment. So Bioid's quite a constrained data set, and the environments don't vary greatly, so it makes sense that it's only learned a few. Well, so it focuses on the environment rather than the actual objects taking part in the action. Here is a frame from a UCF 101 video, and this is an excitation map generated from the temporal network. So this video shows a horse walking along in the centre of the video, and this seems like quite a reasonable result. So the next steps from here are to produce excitation backprop videos from Bioid and UCF 101, both the spatial and the temporal streams, and determine whether the spatial streams determine what the network is looking at in the spatial streams, and the and to determine what the temporal network is looking at in these videos. What will be particularly interesting is to see what happens when the camera moves and an action is being performed during that camera movement. So ideally we want the network to be looking at the action and not the surrounding motion. So once I've produced these, I want to find out so with the Bioid data set, we actually have gaze data for what the person is looking at when they are performing actions. To quantitatively assess the network performance, we can compare the excitation map to the histogram of gaze data recorded to determine how similar the gaze of the person is to the gaze of the network. And this will allow us to assess how similar people are to the neural networks and what they're looking at.